Part 3 of Unit 5 is about electron configurations. Electron configurations describe the distribution of electrons among energy levels, sublevels, and orbitals of an atom. It tells us where the electrons are. Each orbital of an atom contains 2 electrons. And this rule called the Aufbau principle says that orbitals of the lowest energy are going to be filled first. So I've got a picture of what's called an Aufbau diagram. Each of these boxes represents an orbital. And remember, each orbital can hold 2 electrons. And the 1s orbital has the lowest amount of energy. And as we go up this chart, we're going into orbitals of increasing energy. So we start filling 2 electrons per box at the bottom of this diagram and go up the chart from low to high energy. Now before I show an example of that, we need to talk about the 4th quantum number. I know I said there were only 3 last time, but this one's really easy. In the 1920s, it was discovered that 2 electrons in the same orbital don't have exactly the same energy. The spin of an electron describes its magnetic field, which affects its energy. This led to developing ms, the magnetic spin number of an electron, and ms has a value of either -1/2 or +1/2, one for each electron in an orbital. So there's 2 electrons per orbital, and they're not going to be exactly the same. Their spin is different, their ms value is different. One is going to be -1/2, and the other is going to be +1/2. In an Aufbau diagram, we'll represent the electrons with different spins with up and down arrows. There are also 2 more rules in addition to the Aufbau principle we need to follow when we're filling out an Aufbau diagram. We have to pay attention to the Pauli exclusion principle. It says that no 2 electrons can have the same energy, so each orbital can't have 2 electrons of the same spin. Each orbital has to have 1 up and 1 down arrow, or 1 positive and 1 negative spin electron. And we have to follow Hund's rule, which says that orbitals in a sublevel are filled with 1 type of spin in all orbitals first, then the other. That means we're going to fill all the up arrows in a sublevel first, and then go back and fill in all the down arrows. All the positive spin first, and then we go back and fill in all the negative spin. So let's look at some examples about filling out this Aufbau diagram. Let's look at a helium atom. Helium has 2 electrons. So what we're going to do is start at the bottom of this energy diagram. We're going to draw 2 arrows. 1 arrow represents 1 electron. So our first arrow is going to point up. That's our positive electron. And then we're going to fill out this orbital with the other arrow pointing down. This is our +1/2 and -1/2 spin of the electron. And that's it. That's all we have to do for helium, because there was only 2 electrons. If we were looking at neon, a neon atom has 10 electrons. So that means we have to put 10 arrows on this chart representing those 10 electrons. So I'll go ahead and leave these 2 here. I'll put 3 and 4 in this 2s box. And before we go up to 3s, we have to come over here to the 2p sublevel, because it's got energy between the 2s and the 3s. And we have to follow those 2 rules that we just saw. We're going to fill out all the up arrows first, and then go back and fill out the down arrows. So we've got 2, 4, 5, 6, 7, 8, 9, 10. Those are the locations of all the electrons in a neon atom. Let's look at a nitrogen atom. Nitrogen has 7 electrons. So we'll start at the bottom again. 1, 2, 3, 4 electrons. Now remember, we're going to fill out all the up arrows first. 5, 6, 7. So we've got 1 electron each in the 3 orbitals of the 2p sublevel. Let's look at a fluoride ion. We know that a fluorine atom has 9 electrons, but because we're looking at the fluoride ion, it's got a -1 charge. That means we're going to have to add 1 electron. So the normal atom has 9 plus 1 from that -1 charge. We've got 10 electrons in a fluoride atom. So we have to put 10 arrows on this chart. 2, 4, 5, 6, 7, 8, 9, 10. Hopefully you noticed that this looks identical to the electron configuration for a neon atom. Whenever atoms form ions, what they are trying to do is attain a noble gas electron configuration. So a fluorine atom would look like this with only 2 of the orbitals filled. But for it to go from an atom to an ion, it's going to gain that last electron, and it's going to end up with the same electron configuration as neon. Let's look at one more. Let's look at a sodium atom. Well, a sodium atom has 11 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we were going to turn this sodium atom into a sodium ion has a charge of +1. So that means it's going to lose an electron and end up with 10 of them. So to do that, we just give away this valence electron, the outermost one, and we end up with a noble gas configuration. It's got the same electron configuration as a neon atom or as that fluoride ion. So that's several examples of how we use an Aufbau diagram to show the locations of all the electrons in an atom or ion. Now, several times you're going to be asked to write an electron configuration, and that doesn't mean you have to have the Aufbau diagram memorized and have to draw that chart. That would take up way too much room. So we've come up with a way of writing an abbreviation for them. So we're going to look at the same examples that we did on the other page. Helium had 2 electrons, and if you remember, it filled up the 1s orbital, the 1 orbital in the 1s sublevel. So the electron configuration for helium is 1s2. This coefficient tells us the principal energy level, the quantum number n. The letter tells us the type of sublevel we have. That's L, the angular momentum quantum number. And this exponent is the number of electrons present in that sublevel. So, if you noticed on the other page that all of the s sublevels only had 1 orbital, that means the highest exponent we can have on an s is 2. We can only fit 2 electrons in an s sublevel because there's only 1 orbital there. Let's look at neon. The electron configuration for neon, it's going to start off the same way as helium. 1s2, taking out the lowest energy. Then the next step on the chart was the 2s sublevel, and we filled it up with 2 electrons. Now before we went to the 3s, we had to go to the 2p sublevel. And if you remember, there were 3 boxes. That means there were 3 orbitals. Each orbital holds 2 electrons, and we filled it. So that means there were 6 electrons there. This is the electron configuration for neon. A way to check this, we know that neon had 10 electrons. We can add up the exponents and make sure they equal 10. 2 plus 2 is 4, plus 6 is 10. So that's it. That's all we need to do for neon's electron configuration. If we look at nitrogen, it's got 7 electrons. Again, it's going to start off the same way. 1s2. 2s2 fills out the lowest 2 sublevels. And then that takes care of the first 4 electrons. Then we have to go to the 2p sublevel. And if you remember, there were just 3 up arrows in the 2p sublevel. We don't have to show the way they were spinning. We just have to put the total number of electrons that was present. So 2p3 is how the electron configuration for nitrogen ends. Let's look at the fluoride ion. Fluorine, just the atom, has 9 electrons. Starts out the same way. So take care of the first 4, and then to get the 9 electrons, we're going to put 2p5. But since we're talking about the fluoride ion with a -1 charge, this 5 becomes a 6, and it's got an identical electron configuration to neon. And then let's see if I can fit sodium down here at the bottom. A sodium atom has 11 electrons, 1s2, 2s2. It's going to fill out the 2p sublevel, 2p6, that's 10. Then we're going to have 1 electron in the 3s sublevel, it'll end in a 3s1. Now for this to become a sodium ion with a +1 charge, it's going to lose this 3s1 electron. So again, it also ends up with the same electron configuration as the noble gas neon. We can also use the periodic table to help figure out electron configurations. I like to think of this as the board game method. What we need to do is pretend that helium is actually over here in this spot where it should fit. This section of the periodic table, this is called the S block. Remember, helium's not right here. This section on the periodic table is called the P block. The transition metals in the middle, that's the D block. Sounds like prison. And down here, the lanthanides and actinides, this is called the F block of the periodic table. Now, the way we can treat this like a board game, we treat hydrogen like it's go on a Monopoly game. We're going to start counting at hydrogen, and like you're moving a board game piece across a board game, you're going to be counting spaces on the periodic table. One thing we need to remember, the coefficient for the letters in our electron configuration, or the principal energy level, that's just given by how far down the periodic table you go. This is 1, 2, 3, all the way down to 7. The value of the coefficients for the D block are going to be S minus 1. So that means right here, starting at potassium, this would be the 4s sublevel. If we were counting across like a board game, once we go from calcium to scandium, it's going to become the 3d. It's going to be one less than whatever that s value was. And down here at the F sublevel, it's going to be S minus 2. So if we were looking at the 6th principal energy level, this would be 6s1, 6s2, and then jumping down to lanthanum, this would be 4F. It's going to be 2 less than that S coefficient. Okay, now that I've explained it, let's look at a couple quick examples. We always start at hydrogen. Let's figure out the electron configuration for helium. Our first spot is 1s1, because it's that first block in the 1s, it's that first spot in the 1s block, and then we're going to end on 1s2. We've reached the end of the board. So helium's easy. 1s1, 1s2. We just count all the electrons that our board game piece moves across until we reach the element we're talking about. We can look at neon. 1s1, 1s2. So we've reached the end of the board. So we're going to go back around to the second level. We're going to go 2s1, 2s2. That takes us to beryllium. Now we're going to skip over here. This is the P block, remember, so it's 2p1, 2, 3, 4, 5, 6. So we'd end on 2p6. And let's look at nitrogen real quick. Nitrogen's right here, so we have to start at go. 1s1, 1s2. We've reached the end of a block, so we've got to write that down. Go back around to the second row. 2s1, 2s2. And once we reach here, we go across here. 2p1, 2, 3. It's the third one across the P block, so it's going to end in 2p3. Your question for this section, what is the electron configuration for the calcium ion? Do your best to type it into the answer box.